Hey everybody, Bill Sky, the assembly guy, and this is a follow-on video to the Windows calling assembler language functions from C and C++, but this time we're going to do Linux. Now if you haven't seen the Windows one, I really recommend that you go and look at that because it's really a different way of doing things, and there are some differences between doing things on Windows and doing things on Linux as well as on ARM. So there is going to be a follow-on video on how to do this on ARM assembler language, which is basically Linux. So this is a good introduction to it. And I think just like we did in the Windows version, I think we should just jump right into the code. But before that, why would you want to do this? If you haven't seen the Windows version, why would you want to write assembler language code that then is called by C or C++ or any other higher level language? You can even do it from COBOL. Well, the reason that you want to do that is because maybe you want to put together a really fast sort, a really fast search algorithm. Maybe you've got hardware that you want to interface with and you want to be able to access that hardware. Maybe you've even built your own hardware. Yes, I've done it. You've built your own hardware, and the only way to access that hardware is through assembler language. So if you think this isn't necessary, that's fine. You're wrong, but that's fine. It's another skill you need to learn in assembler language. So let's get right down to the code right now. Okay, so I have Mint Linux up here and running, and you can use any Linux to do this. And we're not going to do it from an assembler point of view. We're going to do it from a C++ point of view. So I actually have some C++ templates here, and I'm just going to use a 32-bit. We're going to stick with 32-bit. And we're also going to do C in this video, so you'll be able to take a look at that later. So let's go ahead and rename that to Linux CPP calling ASM. So let's go ahead and just take a look at that. Now, there are a couple of things that we have to do. We do have our main.cpp file, but we're also going to need a main.asm file. So I'm just going to create a, I'm going to do this on terminal just because it's easier. I'm going to touch let's call them asmfuncs.asm. And that's going to create the ASM file. So there's our ASM funcs right there. And we're also going to have to do something with the make file, because now we're going to have to add an assembler step. So I'm going to go in here and I'm going to edit the make file. And let's take a look at this. So we've got our make file, and the make file is going to compile the C++ program. It's then going to link it here, but one thing it hasn't done is that it hasn't actually created the assembler code yet, or assembled the assembler code. So we're going to call this asmfuncs.o, and that is dependent upon asmfuncs.asm. And what we're going to do there is we're going to say nasm, so we're going to do the assembler. And I believe it is, since we're on 64-bit, we're going to have to do something a little bit different on the make file. So instead of saying elf64 or elf32, we're just going to leave that blank on the assembler. And then we're going to say, so then we'll type in our asmfuncs.asm, and we'll create a listing file. And we will then make the link also dependent upon asmfuncs.o. And on the link, we're going to have to also include asmfuncs.o. And what that means is that, so we're going to assemble it here. So if it hasn't been assembled yet, we'll go ahead and assemble it. Then we're going to go ahead and compile the main.cpp file, and then we're going to go ahead and link them both together. So let's go ahead and save that. Now we might have to make some changes to that. Maybe what we might want to do is also get rid of the asmfuncs.o on the clean and asmfuncs.list also on the clean. So let's go ahead and add those. Okay, now we don't have anything in our asmfuncs.asm file yet, so let's go ahead and create a really simple function in here. And so I'm just going to go ahead and say section.text. Now what I could do here is I could create a section.data, and I could create a section.bss if I like. I don't really need it. Why would I want to do these is if I want to create local data for only my functions. It's kind of a really neat feature. It's kind of like global data for all of my functions. And then what I'm going to do is I'm going to create a function called getAFive, and that's going to do a no-op. But then what it's going to do is it's going to move into RAX the number 5. Now, why am I moving the number 5 into RAX? If you remember when I was talking about functions in previous videos, RAX on 64-bit or EAX on 32-bit, it is the register that always contains the return value of any function. And this, by the way, works the same way in C and C++. When you call a function and you return something, it actually goes into the RAX in 64-bit or EAX in 32-bit, and that's how the return value gets back to the calling program. It's actually really a neat mechanism. But that's also one of the reasons why you can only return one thing at a time, unless, of course, you return a pointer to a structure or an array or something like that. Okay, so I'm going to go ahead and return, and I'm going to put a little comment here, end of getAFive. Again, you don't have to do that, but I kind of like doing that. All right, so let's go ahead and save that. And now I'm going to go back, and actually I think I can probably make it here. So I'm going to make it, and it says instruction not supported in 16-bit mode. So I think what that means is that I have actually assembled that incorrectly. I think there's something wrong in my make file. And then let's go ahead and open up the make file. And let's change that assembler to also include dwarf. And we'll say asmfuncs.asm, asmfuncs.asm.lst. Okay. So now let's go ahead and build it. And there we go. So it built just fine. Now, let's go ahead and let's call that function. So I'm going to open up the CPP file. And the first thing you need to do in the CPP file is you need to let your CPP program know that I'm going to be calling an assembly language program, and how should I call it? Well, the first thing I need to do is I'm going to use the extern, and I'm going to say double quote C, double quote, open brace, long int getAFive, void, semicolon, close brace. Now, let's talk about what this means. The extern means that it's external to this program. It's found somewhere else. It's going to be linked later on. The double quote C double quote means I want to use the standard C calling conventions for calling a function. So that's what that means. The long int, I think I could just say long as well. I don't need the int. What that means is that I want to have return from this function a quad word. Now, if you were dealing with just a 32-bit language or 32-bit compiler, you would just say int, because that's 4 bytes, because that's as big as an integer can get, 4 bytes. 8 times 4 is 32. But long int is actually 8 bytes, 64 bits. So that's why we do that. getAFive, that's the name of the function. I like to put void in there just to document the fact that it's not going to take any arguments. And now let's go ahead and build it. And it built just fine. Notice it assembled it, and then it also it compiled it, the CPP. It didn't have to assemble the ASM functions, ASM funcs, because it was already assembled. Now, one of the things I want to mention in previous assembly language videos that I've done is that we haven't linked using the G++. You need to link with the G++ if you're going, because LD won't link it correctly. So G++ needs to be used as the linker as well. Not only is it used for the linker, it's also used for the compiler. However, the assembler we still use NASM. Okay, so we haven't actually done anything here yet with our function, so let's go ahead and do that. So I'm going to say long return value equals 0. So I'm going to create that 0 value, and then I'm going to call the function. So I'm going to say return value equals getAFive. And then I'm going to say cout return value and let's see how that works. And well, it can't find getAFive. I wonder why. Well, if you take a look at your ASM funcs, you never told the linker that the function getify was globally available. You never said it was global. So, and that means can anybody from outside access it? So for instance, let's say we created a function called do something, but I didn't want anybody to use that function. I was only going to use it within my functions within this file. Well, I don't want this to be global. I want it to be secret. I want it to be part of my program. So that would work fine. However, if I want to make the function available to everybody, I have to say global and then the name of the function. So let's go ahead and get rid of that. Let's build it again, and the problem goes away. Okay, let's run it. Oh, that's the C++, or that's the other assembler. Let's go ahead and run this program. And we get our 5. That is totally awesome. All right, I'm going to leave this window open. Actually, I could close that window, and I could just run all of this from the terminal inside of Genie. So I'm going to right-click, set path from document. So let's just stick with Genie. We'll just use the terminal in Genie. Okay, so that's our very, very first, very, very easy little function. Let's create another function. This one we'll call add2. We'll call this add2. And now one thing I did in the Windows demonstration is I forgot to put the RET at the end of the function in Windows. That caused the program to die horribly. I mean, feet kicking around up in the air. It was a horrible death. So it's always a good idea, well, not a good idea, you must put the return in there, otherwise it just falls through and tries to execute code that really isn't there. Okay, so what we're going to do with add2 is we are going to send 2 arguments to that function. Now let's go back to our main and let's add a statement for our add2. And what this function is going to do is it's going to send 2 numbers to the function add2. So we're going to send 2 numbers. It's just going to simply add those together and it's going to return the sum. I know, a really lame program, but it's going to give us everything we need. And because we're dealing with 64-bit, we're just going to keep saying long, long, long. We're just going to stick with 64-bit numbers. It just makes it easier for this demonstration. Can you send something smaller than a long, long? Of course you can. But we're just going to stick with it for right now. Okay, so I'm going to go ahead and build this just to make sure I didn't type anything in weird. And then I'm going to go ahead and call it. And I'm not going to have it do anything. I just want to make sure the infrastructure of the code is ready to go. I'm going to say return value equals add2. And we're going to say 10, 20. And then I'm just going to copy the C out. Return value from add2. And let's just build it. Oh, again, undefined reference to add2. I've got to come up here and say global add2. And it seems to be good. All right, so let's run it. And we get a funny number. The first number from return to 5 is a 5, but we get a very funny number right here. And that's because the value of RAX is the return value, and we didn't do anything with it in the function. If I wanted to, I could say move to RAX 0, and then return. And then you'll see in the terminal how it's now 0. But we haven't done anything in there. Okay, so the next thing we need to talk about, and I talked about this in the Windows version of these videos, is that in Windows, or I should say in the C standardized calling convention, and it's really not as standardized as I would like it because it's different depending upon the operating system you're dealing with. Windows, when you send an argument, if we take a look at our main.cpp, when we send the number 10 and the number 20 to a function, In 32-bit, it sends those via the stack. However, in 64-bit, it doesn't do it that way. And probably the reason it doesn't do it that way is because there's a lot more registers in the 64-bit processor. So it can use registers up. So what does it actually send? Well, the first argument that is sent is RDI. So the 10 will be found in the RDI register. The 20 will be found in the RSI register. Let's say if I had another one, let's say if I had, and I can do this, if I had 30 and 40, if I had 30, that's in the RDX register. The fourth one would be in the RCX register. The fifth one would be in R8, and the sixth one would be in R9. Any arguments that you have past 6 arguments will be in the stack. And I guess it's because they figured, well, it's much more common to have 6 or less arguments than more than 6. And I would agree with that. I don't think there's a lot of functions out there that have 38 arguments. However, that doesn't mean you can't. So the rest of the arguments, anything greater than 6 arguments, go into the stack, and you can access those. The 7th argument would be an RSP plus 8. The 8th argument would be an RSP plus 16. The 9th argument would be an RSP plus 24. So that'll just continue on. And you can actually test this. What we can do is we're going to go ahead and do this. And let's make sure the assembler, we've got a no op there. Perfect. And let's go ahead and debug it. And I'm going to use the KDBG debugger. All right. Now this will be interesting because it'll be the first time I've shown you a multi-language debugging. So what I'm going to do is I'm going to say open source code. I'm going to click on all files, and there's my main.asms. So I've got it right there. And under add to, I'm going to put a breakpoint. And then I'm going to run the program. And there you go. So now you've got an assembler language program that has those breakpoints. Now let's take a look at where our arguments are. Well, if we go back to the main.cpp, you could see the number 10 is our first argument, the number 20 is our second argument. Well, let's look at RDI. RDI is 10, RSI is 20. Those are our first and second arguments. These are things you just have to write down in your notes and remember. So we can go ahead and step over and move 0 to RAX. You can see RAX down here now has a 0, and then it returns, and now we're back to our C++ program. Kind of cool that we're able to look at both C and C++ and assembler all in the same program. Okay, so we're going to go ahead and finish that up. All right, so now that we know our arguments, before we go on to that, what about 32-bit? If you've got a 32-bit program, how are those set up? Well, in 32-bit, it would be ESP plus 4, ESP plus 8. So each one is 8 bytes, but they're all in the stack. They all start in the stack. So again, you have to look at those values in the stack and then pull them out of the stack. So let me be a little bit more clear on that. So the first argument in this case, if this was 32-bit, the first argument 10 would be located in the ESP plus 4 position. And ESP is the stack pointer for 32-bit. The second argument 20 would be in ESP plus 8. The third argument, if we had one, that would be an ESP plus 12. The fourth argument would be an ESP plus 16, and so forth. In 32-bit, they never store them. The C standard is never to store them in registers like it is in 64-bit. I know, it's confusing, but that's the change. And that's why moving from 32-bit to 64-bit could be a challenge, because you've got to change the way that arguments are moved around. But we're going to stick with 64-bit. And I suggest that you take a look at the 32-bit and try it out yourself. Okay, so let's go back to our functions and let's do something with it. Okay, so because our first argument is located what was it? Well, I think the argument was RDI. I believe it was RDI. So what we're going to do is to add the two numbers together, we're going to move into RAX RDI. That's our first argument. Now let's add the second argument. So we're going to say add RAX RSI. And then we're just going to go ahead and return. Now, notice we're modifying RAX inside of the function just like we did in here. Well, that's okay because RAX is assumed to be modified whenever a function is called. So your calling program, if it's an assembler language program, you need to save RAX before you actually call the function. But in this case, we don't have to worry about it. Okay, so let's go ahead and build this. And I'm just going to run it. Let's see if we get 10. Let's look at our C++ code. And it should add together 10 and 20. And Genie's being a little bit funny. And there we go, 10 and 20. So our add 2 worked. Awesome. So we called a function and it returned 30 in RAX, which then moves it into return value. Now let's do another one. What I would like to do is I would like to do a sum array. So I'm going to create an extern C, and it's going to return a long int, and I'm going to call this add array. And what this is going to do is this is going to send an array to the function and also send the number of items in the array. So how would we call this? Well, let's create our array. So I'm going to create a long array called an array. And let's make it just 5 in size. And let's put some numbers in it. So there's our long array. And then how will we call it? So I'm going to say return value equals add array. And I'm going to put the array name and the number of items in the array. It would really actually be a whole lot better to use constants, but we can fix that up later on. So the return value from add array is return value. Okay, so we want to create a function called add array. It's going to take 2 arguments, so we're going to use RDI and RSI as our arguments. Again, if it was 32-bit, you would be putting them in ESP plus 4 and then ESP plus 8. Okay, so I don't get bitten again. I'm going to say add array as a global. And let's create our add array function. Let's stick a no-op in there just so we have a place for our breakpoint. Okay, so now let's move our first argument into an address. We want to move our first argument into a register that's going to be used for accessing the address of that data. So what I'm going to do is I'm going to move into RCX our second argument, and that's RSI. Move the second argument. Now, why am I moving the second argument first? Well, because I need to move into RSI RDI. So you got to think about this a little bit. Now, also, what are we doing here? We're modifying RSI and RCX. So we might want to push RCX and then push RSI before we do that. So before the program ends, we pop RSI and we pop RCX. Because we're modifying those 2 registers, we may want to back them up before we go back to the main. Always a good practice. Okay, so we put RSI, we put the second argument into our counter, and then we put the address of the array into RSI. So I'm going to say a loop. So now I'm going to create a loop here. And that's our loop. So it's going to loop RCX times. All right, so we might also want to zero out RAX. And now let's go ahead and loop through this. So I'm going to add to RAX the dereferenced RSI. Add an array value. And now let's go to the next array position. So I'm going to add RSI 8. Now I have had people ask me, well, if I'm modifying RAX, why don't I back it up? Well, it's a little bit of a problem. If I back it up and then I add everything up into RAX and then I recover it using pop, haven't I just reversed everything I did in the loop? And remember, RAX is expected to be changed in a function. All right, great. So I think that's our code. That is exactly our code. So let's go ahead and build it. And let's run it. And it should be 150, and it is. You can see the 150 there. So this time what we did was we actually wrote a function that took an address of an array. Now, the other thing I could have done is instead of saying square bracket, I could have just said asterisk. And we would get the exact same outcome. Because an array in C and C++ is actually just a pointer to the first item in that array, which happens to be a long asterisk asterisk. All right, let's try this with C next. Okay, so let's do the same thing with the C program. So I'm going to start from scratch again. And the C program is going to be quite a bit like the C++. So if you jumped to this part of the video and you didn't watch the C++ version, you really should. So I'm going to go to the C library here, and let's do 64-bit again. Or the C template, it's not library. And let's rename this to C, calling ASM. So we're basically going to do everything we did in the C++ version. In fact, to make this a little bit faster, no, let's start from scratch. I was going to copy from the C++, but if some of you jump to here, so let's go ahead and change the makefile. That's the first thing I want to do. So let's open this with my Genie editor, and let's change the makefile first of all, because I want to be able to make my program as quickly as I can. So the makefile, we've got everything here. We've got the main.o, but we're also going to need an asmfuncs.o. That's going to be the object file that we're going to put our functions in. Put that down here in the link. Notice we're not using LD for the linker anymore. We're using GCC because when you have a C program, you must use GCC because it uses a lot of C libraries. And then we're compiling the main.cpp, but we also want to assemble the asmfuncs.o. So I'm going to create an asmfuncs.o section here, and I'm going to make that dependent upon asmfuncs.asm. And then we're going to NASM that. And let's just do an ELF32 dwarf asmfuncs.asm and listing files asmfuncs.list. I believe that's what it is, but we'll see it in a little while. Okay, so let's go ahead and do some removing asmfuncs.o, and this is for the clean. LST. Okay, so I think that should be enough for the, oh, and wait a minute, we're 64-bit. I'm not sure what I'm doing here with 32-bit, so we're definitely 64-bit. Okay, great. All right, so let's go ahead and let's see, we've got our C program. Let's create our asmfuncs. So we'll go ahead and create that. And let's go ahead and do the same thing we did in the C++. So what I'm going to do is I'm going to say section.text, and if you didn't watch the C++ version, you need to specify what functions are going to be global to everybody, be able to access them from the outside. So I'm going to say global get file. Now, I'm not going to do all the same functions that I did in C++ because the code is identical. There's a little bit of change to the C code, which we'll see, excuse the pun, but it's pretty much the same. So go ahead and take a look at the C++ one if you jump to this one to see how to send arrays, how to send multiple arguments to a function in assembly language, because like I said, it's the same. So I'm going to put a no op there. I'm also going to put a return, and I'm going to say end get 5. Of course, you don't need that. And then all this is going to do is it's going to move into RAX the number 5. That's all it's going to do. Again, for more explanation, go ahead and see the C++ version of this video. And let's go back to our make file. Now let's go ahead and open up our C program. And just like in the C++ version, we have to say extern for every function that we want to access. So in the case of asmfuncs, I want to access the get5. So it's going to return a long, again, because that's 64 bits. So it's going to return a long get5. We're going to send no data to it. And now let's go ahead and make our project. Okay, looks good. Let me go ahead and run it. It's going to do nothing but say hello world. Yep, okay. So now let's go ahead and call the function. So the first thing I'm going to do is I'm going to create a variable, a long variable called return value. And then I'm going to call the function. And I'm going to say printf return value from get5 is. Now printf is different than cout. You've got to specify in the printf exactly what the data is that you're going to want to print. So I'm going to say %LLU. The L stands for long, the L stands for long, so it's a long, and the U stands for unsigned. I could just say long if I want, but let's leave it unsigned. And the percentage thing, the percentage character says that the next characters up to and not including the following space is to be used to specify what type of data I'm going to print, followed by the actual data that I'm going to print. Now, one thing that we do want to do here is that I want to put a \n to go to the next line. Let's go back and do the make. There we go. Undefined reference to get5. So there's get5. Oh, same thing we did in C++. In the C++ version, it looks like the function name is global get5. So we need to do it this way. You just say the global get5, and then we have to say get5. That was the first time I've ever done that one before. Okay, let's go ahead and open up our main.c because I inadvertently closed it. Let's make it. Oh, looks good. Let's go ahead and run it. And there you go, there's the 5. So again, the other code about sending 2 arguments or even 1 argument to send an array, take a look at that in the C++ part of this video if you haven't done that, and it's identical. The only difference is that the make file is using GCC instead of G++. We're using C programs in the C program or C source code. In the C source code, we're using standard IO instead of IOstream. And also we're using printf instead of prints. Well, I shouldn't say that because in the Windows version we were using prints or puts, but we're using printf here and then this little thing. And oh, by the way, regarding printf, I am doing a set of C videos, and I'm very close to finishing both the printf and the scanf functions within C, which is kind of synonymous with cout, count, and cin. So you can watch those videos to get more information about how to do those. Okay, so that is sending arguments to, actually, yeah, I guess it is that too, but it's calling assembly language functions from programs written in C and C++. I hope you enjoyed this video. There's going to be an ARM version of this video sometime in the near future. I'm a little bit behind on my ARM videos, hoping to get up to that. We're also going to have something like this in my COBOL videos. How can you call a C and C++ program in both COBOL and Fortran? Hope to see you soon.